Okay, hello and welcome back to this online lecture for my HEP 112 class, Logic and Philosophy. Primarily, this video is intended for students in that class. So we are now turning our attention towards natural deduction in the class. And by way of introduction, we may remember that back at the beginning of this, we said there was really two ways to look at the formal language that, or any language actually, but in particular the formal language that we were talking about, which is in terms of the semantics and the syntax. So remember that the syntax tells you what symbols you're allowed to write. So for us, it's capital letters. And we were allowed to write things like tilde and wedge and the dot and the horseshoe. Um, and we had our parentheses, the curly brackets, we had square brackets and regular parentheses, as well as the ones on the other end there. Um, so this, and then we had rules for forming sentences out of this, which said things like if you have P as being a well-formed formula, then tilde P is a well-formed formula. And if you have P and Q as well-formed formulas, then P wedge Q is well-formed, P dot Q is well-formed, and P horseshoe Q is well-formed. And then you can go ahead and introduce some conventions governing these brackets and parentheses here. And we can say that whenever it's ambiguous what the main operator is, then you need one of these things around. So if you wanted to say P wedge parentheses Q dot R, then that would be distinct from P wedge Q dot R. And so then we said that the main operator was any of these operators which is outside of the parentheses, unless of course there's more than one operator outside of the parentheses. As for example, if you had a tilde parentheses P horseshoe Q or parentheses P horseshoe R, just making stuff up here. So here we have two operators outside of all the parentheses, the tilde and the wedge. And so in this case, then it's not the tilde that's the main operator. And so, okay, then that was basically how we stipulated our syntax. And then we looked at some ways to translate English sentences into these arrangements of symbols. And then when we were asked what the meaning of these things is, what we said is that A, B, and C, etc., stand for propositions. And propositions can have truth values. And the truth values for classical logic are true and false. We looked at last time what happens if you introduce an in-between value here. We said that the propositions can be either true or false. And then we sort of assumed in the background that every proposition is true or false, so that, in other words, for any proposition, either it or its negation is going to be true. And then we also assume that it's not the case that you ever find it's not the case that you ever find some sentence and its negation, which is both going to be true. So these are said to be governing our truth values, basically the law of the excluded middle and the law of non-contradiction. And then we defined all of these operators over here in terms of functions which operate on the truth values of propositions. So you may remember that if we said if you have a proposition, that proposition can either be true or false. And if you apply a tilde to that proposition, then the tilde takes that true and returns it as false, and takes this false and returns it as true. And then, in fact, each one of these was defined in that way, according to the truth table over here. And all of this is to say that the meaning of these things for us was given in terms of these truth functions. So the basic idea that the letters stand for propositions and the operators are truth functional. So then we went on to prove that there were some valid argument forms. You may recall the last time we looked at modus ponens. Um, this is a valid argument form. If you know that P horseshoe Q and you also know that P is true, then you're allowed to infer that Q. We looked at modus tollens, if you remember. Um, and then we also had a couple of others, like, for example, disjunctive syllogism and hypothetical syllogism. And we'll be talking more about those in just a second. But we said that these were kind of like basic argument form patterns, which you could prove were valid using the truth table definitions of these operators that we have here. So if you remember, if you have P and also Q, and then you say P horseshoe Q, then this is going to be a false when P is true, but Q is false, and true in every other case. And then using these two definitions, you could prove that these argument forms down here are, are valid. And we looked at 8 kind of argument forms, 6 of them that were valid and 2 of them that were invalid. And so now we're sort of going to be switching over from the semantic side of things, where we're talking about truth tables, to the syntactic side of things, where we'll be talking about proofs. Okay, so in logic, proof is considered to be a syntactic relationship. We even have fancy symbols that you'll see, and I'll talk about them maybe later. We don't have to worry about them right now. But one thing that we can kind of notice is that when we defined modus ponens and modus tollens, that we did so in what seems to be a purely syntactic way, saying that if you have some well-formed formula followed by a horseshoe and then some other well-formed formula, and you also think that that well-formed formula in the first part is in fact true, then you can kind of detach the Q part. You can get rid of the horseshoe and bring the Q part to exist by itself. So in a way, it's like getting rid of the horseshoe. And modus tollens is doing something similar, but it introduces the tilde sign. So it's almost like these rules are defined in a sense by their syntactic structure. And so when we switch over to talk about what's called natural deduction, which is the topic of today's discussion, natural deduction is a proof procedure. So it allows you to prove that certain propositions follow from certain other propositions so that you can prove that an argument is valid, for example. It's not, technically speaking, what we would call a decision procedure. A decision procedure, sometimes in logic, is referred to as something which could tell you in every case whether an argument is valid or invalid. Truth tables are decision procedure, but these ones focus only on valid arguments. So for the next little bit, we're going to just focus on how you could prove that a argument entailed its conclusion. So basically, what you want to do when you have a proof is you want to be able to start from the premises, whatever they are. And you want to be able to show that by using only the rules of logic, um, that you could get the conclusion to follow from those rules of logic plus the premises. So remember, we always kind of start with the assumption that the premises are true and see where we can go from there. So when we're doing natural deduction, we also are going to be taking that same idea that whenever someone gives us an argument, the first thing we do is say, okay, so is it valid? We assume that the premises are true, and then we try to reason our way to get to the conclusion. And if we can do that, then the argument's valid. Okay, so now, of course, these rules of logic, what we just saw is that we already have a couple of intuitive rules. So we have modus ponens, we have modus tollens, which says if Q is necessary for P, but Q itself is false, then P must be false, because if you had P around, then you would have had Q, since P horseshoe Q is true. And then we also saw disjunctive syllogism, where if you know that P or Q and also tilde P, you can get Q. And then finally, we have our hypothetical syllogism, which says if you think that P horseshoe Q and Q horseshoe R, then you get P horseshoe R. So these are sometimes called rules of implication. In the book that we're using, these are the first four that are introduced. And really, this is really all that we're going to be doing. We're not going to go too much deeper than this. We'll talk about a little bit of the applications of these things, um, like for conditional proof and how you can build computers using these ideas. So we're going to come back to that. But for right now, and maybe axiomatic systems we'll mention very briefly towards the end. But for right now, we just want to kind of understand these things because what we're going to be doing is importing them into our proof procedure. And what we're going to say basically is that if you have some premises and you want to prove that the conclusion follows from those premises, then you should be able to do it by starting from those premises and applying one of these rules in a systematic chain-like way until you get to the conclusion. Okay, so that's what a proof procedure allows you to do. And natural deduction is designed in such a way that it's supposed to mimic, in some sense, the way ordinary reasoning in this area kind of proceeds. So whether that's true or not, people can debate. Okay, so having said that, then we want to look at some examples. We're going to keep in mind that we're going to think of these four rules and draw on our experience from last week, whereby we interpret some certain arguments as having this structure or not having this structure. So there were a couple of arguments in the book, and later on we'll do some examples from the textbook, which is going to be what your homework is based on. So the first example from the book, I have my book open here. Remember, we're using, oops, I didn't mean to do that. I don't know how I did that. I accidentally clicked on something and it made it much bigger. Okay, so what I wanted to do actually was minimize this, not make it bigger. Because I have my book open here. This is Hurley we're using, a concise introduction. And there are various reasons for using that book, but okay. So I have it open behind the screen here so I can read from it. So if you have yours, if you're in the class or you have it from some other reason, then this is on page 338. So the argument there says, if the Astros switch leagues, then the Braves will not win the pennant. So if you take A and call that the Astros switch leagues, Astros switch leagues. And if you take B, the Braves will win the pennant. Braves win pennant. So the first sentence there we could say says, if A happens, then B will not happen. The second sentence says, if the Cubs retain their manager, then the Braves will win the pennant. So that's C is Cubs retain manager. So that one said, if C, then B happens. The Astros will switch leagues. That's that we have a premise as A. And the conclusion here, therefore, the Cubs will not retain their manager. So it's customary to write a slash over here, and that would be tilde C. Okay, so using this key, then that argument, if the Astros switch leagues, then the Braves will not win the pennant. If the Cubs retain their manager, then the Braves will win the pennant. The Astros do, in fact, switch leagues, and therefore the Cubs will not retain their manager. Okay, so now we translated it into symbolic form. We'll do some more examples that come from the textbook later. This right here is, they explain this in a textbook, but I think sometimes it's useful to go over it even so. Okay, so what we want to do is what we call derive the conclusion. So to derive is to arrive at that conclusion by application of the rules of logic that we have at our disposal. So in this case, what we have are just these four rules here. And the four rules are the ones that I was already explaining and that we've already been talking about. That's modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. So now a useful strategy for being able to do this on your own is to look at the conclusion and then see where you find it in the premises. So we see tilde C is the conclusion. And then we look around and we see, well, we don't have any tilde C's around. So it's not just like hanging out like tilde B is. Um, on the other hand, we sort of see that there is on the second line here a C. And we can see that the conclusion is just that, but with a tilde in front of it. So you might be thinking to yourself, aha, you see, modus tollens allows you to put a tilde in front of some well-formed formula as long as you have it connected to a horseshoe to some other well-formed formula, and there's a tilde in front of that. See, now notice how what I'm doing here is I've switched gears completely to talking about these in a syntactic way. All I'm talking about is whether there's a horseshoe as the main operator, whether there's a tilde in front of the thing that's the consequent, just things that are syntactically defined. And in fact, you can kind of see that here, this says C horseshoe B. So if you wanted to construct a modus tollens, you would have to have C horseshoe B and then a tilde of the B thing, because in this case, P is C and Q is B. And if you had that, then you could get tilde C. And of course, you can see tilde B is in fact there on the first line, connected by a horseshoe to A. So it's intuitive that this argument is saying, look, if A happens, then you get not B, and A is true. So you should be able to get not B. And if you have not B, then you get not C by modus tollens. So now what we can do is construct a proof which kind of goes through that reasoning. And what we will do is we will start with our numbered lines, and we will add another numbered line here. And what we are trying to do is to have a numbered line where tilde C is written down. Now notice there's no number, there's a slash here. So the goal is to get this written down with a number on it, because remember that according to us, when we write these numbers down, what that symbolizes is that someone has asserted this sentence, like we're taking it as a premise and as assumption. And when we write new numbers down, what we're saying is that they follow from these assumptions. So lines 1, 2, and 3 are our assumptions, the premises. And then we're going to use these rules to try to interpret these things in such a way that we can produce tilde C. And it's not too hard. If we look at line 1, says A horseshoe tilde B, and we want to get tilde B down. That's kind of what we said informally. And we can see that modus ponens, if you take the P term to be A and the Q term to be tilde B, then line 1 here says P horseshoe Q, because now this we're thinking of as P, and then this over here is the Q part. So now we're thinking of these in this way, in which case this sentence can be read as the first premise of modus ponens. And then since on line 3, we have A written down again, that's the second line of modus ponens taken together with line 1. So what we can do then is we can write down here on line 4, we can say, well, look, if these 3 sentences are true, then tilde B also has to be true. Why? Because lines 1 and 3 together form a version of modus ponens. So we don't have to write this part, but as long as you think of the A part as being P and the tilde B part as being Q, then line 1 says P horseshoe Q, and line 3 says P, and the conclusion of modus tollens is therefore Q. So we could write down tilde B. Okay, so now we've moved one logical step, and now we can see we can do the same thing now, because now we're looking at these lines, and we're trying to enact this kind of informal strategy that we had. We can add a new line, And whatever we write on this new line is going to be the conclusion of one of these arguments up here. And there's going to be some other lines we wrote down that are going to be the premises. So now our goal to get tilde C over here, we can see that, remember that we could get tilde C by modus tollens if we thought of the P term as being C and the Q term as being B. Then tilde Q would be tilde B, which we have on line 4. So now lines 2 and 4 together form a version of modus tollens. This says P horseshoe Q, taken this way, and this says tilde B, taken that way. And the conclusion, tilde Q, in this case would be tilde C, in which case we are done. We have now formally proved that the argument is valid by constructing a step-by-step derivation starting from the premises of the argument and proceeding to the conclusion. Now, of course, it still will be an open question whether those 3 premises are true, but what we have shown is that if they are true, then the conclusion is true, because if you start from the assumption of the premises, oh, I should write down here, by the way, that this came from lines 2 and 4 by modus tollens. So this way of constructing proofs is a traditional way of doing it. There's nothing magic about it. We're just showing anyone who came along what the reasoning process was and how we got to where we are, because someone could look at this and say, okay, so they started with these assumptions. That's what this slash here means. And then they use modus ponens, and they can check for themselves and say, yeah, that does make modus ponens. And then they use what they got from modus ponens to do modus tollens, and that got you to the conclusion. So that is how you do natural deduction. It's a step-by-step application of these things that we're taking as kind of basic. Now, of course, we know why we're taking them as basic. We think that modus ponens and modus tollens are intuitively valid. And the whole kind of classical logical tradition is based on the idea that these are valid argument forms, and the definitions that we gave in terms of truth tables bears that out. But we've also seen that there's other ways to define those things, as when we talked about alternative logic. So we don't need to rehash all that stuff now. But nonetheless, it's good to keep it in mind. All right, so let's look at another example coming from the textbook here. So this one we can take as already symbolized. This one says, if you know that A horseshoes B, and the second line says tilde A horseshoe C wedge D, and line 3 says tilde B, and line 4 says tilde C, and the conclusion, I can't see it, is D. Okay. So once again, the goal here is to provide a step-by-step deduction starting from these 4 assumptions and applying only these rules up here in order to produce D written down on some numbered line. So the first thing that we should do is kind of think about where we see D. And here you can see that D is connected by a horseshoe to tilde A. So this is the main operator. Over here we have C wedge D. And what we would like to do is write C wedge D on a line down here, because there clearly is a D part. And if you remember our disjunctive syllogism rule, it says you can break apart a wedge as long as you have something with the main operator as a wedge and a negation of the left-hand part of it, then you get to write down whatever's on the right-hand side. So D is on the right-hand side there, and we would need tilde C in order to do disjunctive syllogism, because in that case, P would be C and Q would be D. So P wedge Q is C wedge D, and tilde P is tilde C, and Q would be D. So that would be how we would connect that up. So that allows us to see that what we would like is to get C wedge D written on a line by itself down here. Now, This connected by a horseshoe, we know that we have rules that tell us about horseshoes, and that's modus ponens and modus tollens. So what we want is to have C wedge D, which if you look at line 2 and you think of the P term as being tilde A and the Q term as being C wedge D, then line 2 says P horseshoe Q, because now this whole thing over here is P, and this whole thing inside the parentheses is Q, and the main operator is the horseshoe. So we could think of that sentence as saying P horseshoe Q. In which case, if we wanted to get the Q part, modus ponens is our useful tool for breaking apart a horseshoe. In some systems, they call this implication elimination or horseshoe elimination or whatever. So, because there is a way in which this is like getting rid of the horseshoe, you can take apart the horseshoe as long as you think the antecedent for the horseshoe is true, or in other words, it's written down on another line. Now, of course, in order to do that, we would need the P term to use modus ponens. So we would need tilde A. Okay, so we don't see tilde A anywhere, but we can see this says A horseshoe B. And A is the antecedent. So if you wanted to put a tilde in front of there, modus tollens would be your best bet, because modus tollens says if you have P horseshoe and Q and you can say tilde Q, then you'll get a tilde in front of the antecedent. And of course, that would mean we need tilde B, but we have that written down. So we know what we can do basically. We would take tilde B, because A horseshoe tilde B together with, A horseshoe B. Oh my gosh, sorry. I'm thinking a step ahead over here, obviously. So A horseshoe B together with tilde B makes a version of modus tollens. And so we could write that tilde A is the conclusion. We write the conclusion down on a new line because it logically follows from these assumptions. As long as you recognize that lines 1 and also lines 3 make a version of modus ponens. Okay, so on the right-hand side, you should always think of yourself as writing an answer to the question. And the answer to the question is, by what authority do you write down this sentence tilde A? And over here, you're responding, well, because lines 1 and 3 make modus ponens. And modus ponens is a rule that I'm allowed to use because I'm allowed to use any one of these ones up here. Now, once you have tilde A, then you could see you could use modus ponens again, because lines 2 and this new line 5 will give you C wedge D by another application of modus ponens, as long as P equals tilde A. And I already wrote this and just erased it, but as long as this is how you're thinking of line 2, then this is the P part. It's tilde A. So you're allowed to write C wedge D down on a line by itself because lines 2 and 5 make modus ponens. So this is just an application of the rule, modus ponens, but now specifically picking out lines 2 and 5 and showing how they together make modus ponens. The fact that there's all these other premises there don't matter. These two all by themselves logically imply the conclusion. And of course, once you've gone there, then we know on line 7, what we can write down is that D follows from this, because line 6 over here and line 4 and line 6 form disjunctive syllogism, as long as you recognize that P in this case is C and Q in this case is D, then line 6 says P wedge Q, and line 4 says tilde P, and the conclusion is Q. So that's the power of using these rules, is now instead of what is this, A, B, C, and D? So that, to do a truth table on this would require 16 lines, 2 to the 4. It's not the end of the world, but it's still not exactly fun. But this, just a few steps, shows how the conclusion logically follows, because you would kind of reason your way towards the conclusion, saying, well, If A, then B is true, and not B is true, then I get not A. And that, if I have not A, then I get C wedge D, so I do. And I had already thought that not C was true, so I get D. So this natural reduction is supposed to be, in some sense, mimic the way ordinary um, the way ordinary thought is thought to proceed in these cases. So that's all very good and wonderful. So you may have noticed that the kind of strategy that we're developing here is to kind of get used to thinking of the rules that we have as tools that do things. So instead of having like a can opener or a screwdriver or a hammer, so instead of having those sorts of things, now what we have is modus ponens, which is like our screwdriver, and modus tollens, which is like a hammer, and disjunctive syllogism, which is like a measuring tape. I don't know. They're like different tools that you can use in the sense that they each have their own function. Modus ponens can be thought of as a way to disconnect the cue part, the consequent of a conditional statement. Modus tollens can be thought of as a way to introduce a tilde into a horseshoe statement, into the antecedent of it. Disjunctive syllogism can be thought of as a way to break apart a wedge. And hypothetical syllogism can be thought of as a way of introducing a new hypothetical statement, new conditional statement, with a horseshoe as the main operator. So that each one of these can be thought of as having a specific function. And it's important to sort of think of them in that way, as having syntactically a given function or structure. Okay, so let's look at a more complicated example. This again is coming from the book. So we're given uh, some symbolized premises. So we have as one premise F horseshoe G, and then we have F wedge H, and then we have tilde G, and then I think we have H horseshoe parentheses G horseshoe I, and then the conclusion we're told that we want is F horseshoe I. Okay, very good. So now we're given this argument. And so we're developing this idea that what we want to do is be able to add numbered lines below using where each one shows how one of these conclusions follow from one of these simple argument patterns, these rules of inference that we're using, until that we get to the conclusion F horseshoe I. And so when you're doing these, as you will have to do them on the exam and in the homeworks, the first thing you want to do is look at the conclusion and think about the four rules that we have. Now, if we were doing this in a more serious way, we would introduce all the rules because ultimately we want is like a set of rules that allows us to prove that for any valid argument that is valid. Okay, so we could say that more formally by the end of this, but for right now, we just want to notice that in order to get F horseshoe I, and if you look around, you don't see F horseshoe I anywhere here. If you really wanted to get F horseshoe I, then if you're looking at the conclusions of these arguments, which are the possible things we could write down, there's only one of them that looks like the conclusion is a horseshoe statement, and that's hypothetical syllogism. So in that case, you would have to think of F horseshoe I as the conclusion of hypothetical syllogism, which means that F would have to be P and I would have to be R, because the horseshoe that you get is P horseshoe R. What that means is that in order to produce that conclusion, what you would have to have is that F horseshoes some well-formed formula, and then that well-formed formula horseshoes I. That's the pattern up here. And all we get from the conclusion is that it must have this pattern. So then the question that we would have is what thing can Q be? So when we look over here, then we want to find some conditional statement that has F as its antecedent. And when we look through each line, we see that, well, that's line one, F horseshoes G. Okay. So that right off the bat gives us the idea that maybe G is the thing that we want to connect these two conditional statements. And in fact, we see on line 4 that inside these parentheses, it says G horseshoe I. Well, that would fit our pattern because if we had F horseshoe G and also G horseshoe I, then the conclusion would be F horseshoe I, just as we would like. So we have one of those already written down on line 1. The question is, can we get G horseshoe I written down? Because as it is, it's inside these parentheses, in a sense, hidden from our use because the main operator here is this horseshoe. And in order to get G horseshoe I written down, we would have to look for something which could break apart the horseshoe. And we see that modus ponens and modus tollens are our options for getting for breaking them apart. In this case, we don't want a tilde, so that looks like modus ponens. And then it looks like in order to make that work, you would have to think of the P term as H and the Q term as G horseshoe I. So remember, P and Q over here in these rules can be any well-formed formula, not just the ones which are single capital letters. So G horseshoe I is a well-formed formula. And if you interpret P and Q that way, then line 4 over here says P horseshoe Q. It says H horseshoe G horseshoe I, so P horseshoe Q. And what that tells us is that in order to do modus ponens, we would need H, and then we would get G horseshoe I. Okay, and then we could do our plan over here. But of course, in order to get H, well, where is H? It's on line 2, and it's connected by a wedge to F. So we look at our rules and we say, well, there's a way to break apart a wedge. That's disjunctive syllogism. And to break apart the wedge, you need a tilde in front of the P part. So if this is P wedge Q, then that means we would need a tilde in front of F. Okay. How are we going to get a tilde in front of F? Well, the only way that we can introduce a tilde that's not there is with modus tollens. But that would mean we need F horseshoe, we need P horseshoe Q and then a tilde of the Q. And of course, we see lines 1 and 3 is giving us that. So if we think of P as being F and Q as being G, then line 1 says P horseshoe Q, and line 3 says tilde Q. And so we could write down on a new line tilde F by lines 1 and 3, making modus tollens. Okay. So now we just kind of work our way backwards to this kind of map that we made over here. Because in line 6, we could say, well, if you know that F wedge H and also that tilde F, then you know that H has to be true because those two lines make disjunctive syllogism. So lines 2 and 5 make disjunctive syllogism. So now we know that H is true given these assumptions. And we already know that if H is true, then G horseshoe I is true. So we can say G horseshoe I. And we could say that that's true because lines 4 and 6 make modus ponens. But of course, if G horseshoe I is true, and also F horseshoe G is true, as line 1 and line 7 say, then we can write down that F horseshoes I, because lines 1 and line 7 make hypothetical syllogism. So now the thing that we wrote down is the same as the conclusion, and that means that we're done. So we would only stop when we wrote the conclusion down and showed how it followed by a step-by-step deduction, how you could derive the conclusion from these premises. Okay, so this one was a little bit more complicated. It required more strategizing, as we might say. But it's doable once you start to really think syntactically in the sense that each one of these is a rule that has a particular purpose for existing. And then our job is to get familiar with those purposes and to be able to apply these rules in this way. Okay, so let's take another example here. Again, coming from the textbook. Okay, so for those who have the textbook open and are following along, this is coming from page 340 of the textbook, which I have open behind the screen. So I'm just copying the argument down and then we'll work on it. So the first premise here says that it's tilde A dot B or brackets tilde E dot F horseshoe parentheses C horseshoe D parentheses bracket. The second is tilde tilde A dot B. And the third premise is tilde parentheses E dot F. The fourth premise here is D horseshoe G, and the conclusion is C horseshoe G. Okay, so now here we have a more complicated set of premises. And this one is a little more advanced than maybe this will be like the kind of stuff on the homeworks that's towards the ends, but it's still something which if you start with the kind of strategical tips that we were just talking about, you can kind of work your way through. So the first thing to do would be to look at the conclusion over here and see, well, okay, so I want C horseshoe G. And you look through here and you see that there's nowhere where C horseshoe G is written down by itself. So if C horseshoe G existed already, then our strategy would be like, okay, so how do we use these rules to get it by itself? But it's not there. So what that tells you is, well, we have to think of hypothetical syllogism because that's the only way that we have to build a horseshoe which doesn't currently already exist written down. So once again, that means we can follow that strategy. So that means that P has to be C and R has to be G. And then the question is, what is Q going to be? Okay. So what we want is to say that C horseshoes something, and that very same thing horseshoes G. And then the question is what? So we can look over here and we see line 4 says D horseshoes G. Okay, so that immediately gives us a clue. Maybe it's D. So if it's C horseshoe D and D horseshoe G, then that would give us the conclusion, but then we would need C horseshoe D. Well, we can see that C horseshoe D is in fact there. It's buried in this sloppily written parentheses, which itself is connected inside of these brackets. So there's nothing we can do because the brackets kind of close off that. The brackets tell us that this statement is a wedge. So that statement 1 really can be thought of as saying that P is tilde A dot B, and Q is tilde E dot F, horseshoe C horseshoe D. Okay, so if you interpret P and Q this way, then this first sentence says P wedge Q, right? So we can interpret that whole big sentence up there as saying P wedge Q, in which case we see that there's a rule that allows us to manipulate wedges, and that rule is this disjunctive syllogism rule. And it says we would need to have a tilde in front of the P thing. So the P thing in this case is tilde parentheses A dot B. So what happens if you put a tilde in front of that? Well, you would have to get tilde tilde A dot B, because now you have this thing with a tilde written in front of it. And that's what you would need as the second premise for disjunctive syllogism. And you can kind of see that that's there already, tilde tilde A dot B. Well, that's lines 1 and 2. You can immediately just kind of jump in here and say lines 1 and 2 make disjunctive syllogism. So I can write down the Q part, which is this thing in brackets. And when we do that, we take off the brackets. So you write tilde parentheses E dot F, because now it's free, and that horseshoes C horseshoe D. And then by justification, we say that we did it because lines 1 and 2 make disjunctive syllogism. Okay. So now remember that the reason why we did that was that first we noticed it, but also um, we were ultimately trying to get this C horseshoe D written on a line by itself so we could connect it with D horseshoe G to get the conclusion. Okay, so now we have something new to use. And we can see that line 5, the main operator here is a horseshoe. So line 5 is a P horseshoe Q situation as long as P is tilde E dot F and as long as Q is C horseshoe D. Then this says P horseshoe Q. Okay, so now if we wanted to get the Q part all by itself, well, we have a rule that allows us to do that, which is the modus ponens rule. And it says, well, if you have a horseshoe and you have the antecedent written down, then you can break off the Q part and write it down. So now we can do that because line 3 says tilde parentheses E dot F, which is our P thing. And line 5 says, if you have that, then you have C horseshoe D. So now we can write down that C horseshoes D. Why? Because lines 3 and 5 make modus ponens. Okay. So now we've almost done what we started out to do. Now we just have to enact our ultimate goal over here because we have C horseshoeing D and we have D horseshoeing G, and that allows us to write that C horseshoes G by hypothetical syllogism on lines 4 and 6. 4 and 6 are hypothetical syllogism. So then we'd be done because the thing we wrote down on line 7 is the conclusion. And every step in between is one that follows from the premises and some application of one of our rules of implication, one of these rules that allow us to move from some premises to some other conclusion. So what we're developing here is kind of like you can think of it as sort of like a word puzzle, a Sudoku, or some kind of game where you're given some moves that you can make, and then you're giving a starting position, and the question becomes, can you get from the starting position to the desired results, which is the conclusion, by only using applications of these rules? And we only have 4 of them, so we're a little bit constrained about what sort of things we can do in those kinds of cases. But that's how that goes.